So today we're going to talk about eventually sound waves, and that's the only thing I'm going to do today. I'm going to skip the thermo. I'm just going to tell you the thermo result that we need, and maybe if I go fast, I'll derive the adiabatic relationship at the end, but it's not as crucial. Like I'm going to tell you P equals rho to the gamma, and we're going to use that. That's the important bit. How you derive it is valuable, but we'll get to that later. So let's first go through, I do need that. Bear with me while I set up my technology. So I'm going to go through the homework. So how do you guys feel about the homework? Pretty straightforward?
Yeah.
Little Ned? My goal with this homework was not to be particularly challenging and just to put things in your face that I need you to know. And to dust off the cobwebs, because I know, how many of you do vector calculus over the summer? I do, but that's because it's my job. Okay, so this isn't my favorite. Does this work? No? Come on. Oh, I gotta fix that. Bear with me. Let me see if... Here, this is going to go crazy, and now let's try the other. There you go. Okay, now, drop on, no hydro. So I'm going to pull up the homework, as provided I can find it.
I was thinking about it. I woke up.
Oh, really?
So now I texted me.
Okay. So let's go through the homework real quick. So why is the curl of gravitational force 0?
Conservative.
Because it's conservative. What does that actually mean? And from the math, what?
You can derive the scalar potential from.
Yeah, it's the gradient of a scalar potential, and the gradient of a scalar is curl free. So that's, you don't even need conservative. You don't need to go. So now, if all you said was conservative, I know that means it's the gradient of a scalar, but that's the important bit, is it's the curl of the gradient of a scalar is 0. Write out this expression in tensor notation. Refer to Appendix A3 if you need a refresher. Let's see, I forget what this is. This says v dot grad v equals grad 1/2 v squared minus del cross v cross omega. So the v dot grad v term is here, and so the things that are important is the v on the outside has the same index as the thing that you're taking the derivative with respect to. So the vk goes with this k. This I is a free index, so there's only one I on any of the terms. So in this term, this is v squared, 1/2 v squared. V squared is just vk, vk. I could use vw, vw. It doesn't matter, because that term gets summed over, so it doesn't exist outside of that term. And there is a grad with respect to xi. So this I has to connect to this I. And then we have this curl of a cross product. So we have epsilon ijk, here's the I, and j, k and l get summed over. So there's a k for the first one and an l for the curl. And then an m goes with the bottom one and an n goes with the top one. Everybody get all of that? I'll go through it, but it should basically look like this. And I'll go through it and give you detailed notes if there aren't any problems with everybody's things. I kind of flipped through the homework, and it looked like basically everybody was on top of stuff. So I'm not going to spend a ton of time with this one. Does anybody have any questions about this equation? Feel all right about index notation? Feel all right about making sure you get the free index, you know which one the free index is and which vector component it's referring to, and which bits get summed over and don't exist anymore. And here, how many sums do we have? We have I is the free index. We have a sum on K, we have a sum on L, we have a sum on M, and we have a sum on N. So there's a lot of sums going on in that term. Okay. Show that an object in solid body rotation, or a flow in a solid body rotation has V equals omega cross X, and omega actually should be a vector. Where omega is big omega z hat. So this is just rotating in this direction, where this is omega z hat, and this is the rotation. So all I asked to do is work out what V is using index notation and the epsilon ijk. So this is just getting you practice with Levi-Civita again. Probably warmed up because I think everybody's mostly seen it. So we go through an epsilon, Vi is epsilon ijk omega j vk. Crunch out a bunch of stuff and you're left with Vx equals minus omega y, and Vy equals omega x. So you can check here if this makes sense, because if you think about an object in solid body rotation, it's rotating like this, and it's rotating faster out here in linear velocity. Same speed in angular velocity, but it's faster in linear velocity. So as I increase, so just think about the x-axis. As I increase this way, the velocity is getting bigger. So the y, Vy, is increasing as you increase x. And that jives with what I got. And similarly, Vx is pointing in this direction, so it's negative, and increases with y. So you can just do some spot checking to make sure that the result that you get makes sense. So Vx is this. And then the last thing we do is find the curl. So let's find the curl of this velocity field. I didn't write anything else useful down. I just wrote down del cross V is 2 omega. So you get a 2 omega. I spent a couple minutes trying to get a good intuition for this, where this 2 comes from. I don't have an intuition that's satisfying, not like my intuition for the rest of the stuff that we'll talk about. So the only thing that I was really thinking about, so when we wrote down our general tensor, pi ij, this is dvi dxj, we broke this into a symmetric and an antisymmetric part by saying this is equal to 1/2 of d I vj plus dj vi plus 1/2 dj vi minus di vj. And we said that this part is the rotation. So you pick up a 1/2. So it comes from the symmetry of the problem. You need a 1/2. That's not a good explanation. But anyway, there's always a 1/2. Or there's always a 2. So you get twice the rotational body is the vorticity. And then div v means that div v is 0, so you find that div v is 0. And that means there's no flux across any surface. So there's no inward or outward radial velocity, because nothing is moving across any given radial surface. This one I'm not going to do because it's a bunch of calculus that I'll mess up if I try to do it on the board, and it's not all that useful. But I will. We can talk about the basic strategy for this one. So show that in cylindrical coordinates, del is r hat d by dr, theta hat 1 over r d by d theta, and z hat d by dz. So how do you do that? Somebody holler something. How did you approach it?
To write it in x, y, z,
Mm-hmm.
and then take the x, y, z that we have here, invert it, and then take the derivatives and just plug it in.
Right. So it's basically, you start off with grad equals d by dx, x hat d by dx plus y hat d by dy plus z hat d by dz. And then I've given you some, I don't think everything that you need, but most of what you need. And you basically just replace d by dx with the chain rule. So this is just an application of chain rule. All I'm stating here is chain rule, and then we have the specifics down here about and up here about the actual coordinates. So you just plug it into chain rule and turn the crank, and out comes what you want. There are more complicated ways to do it as well, but that's the most primitive way to do it. And then second, you show that the divergence of a vector in polar coordinates is this, so you get 1 over r d by dr of r ar, 1 over r d theta a theta plus d a z d z. So how do you do that? You just basically take this and another vector a, and again, remember that your unit vectors change with space. That's an important key point. Unit vectors move around. So the unit vectors are inside the nabla, so you have to take care of that when you do all of your chain rule. So it's a little bit of calculus. I only want to talk about the detail, the important bits, and not the details at the moment. Does anybody have any questions about this one? Everybody feel like it went relatively smoothly? Yeah.
Do the hat vectors always have to come before the partials, like in the gradient?
It's more clear when you write it that way. So I mean, like up here, I started to write d by dx of x hat, but unless I'm careful, that's saying the x hat, the derivative of x hat. So I try to write, when I'm writing something that's just an operator like this, I try to make sure that it's really clear that this is an operator that's not operating on anything. But as far as order, we don't do anything where the order matters too much. Boom, 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 boom. And then, close the book and derive continuity and Euler's. I'm not going to do that again right now, but does anybody have any questions on those derivations? So Euler is basically conservation of mass. The mass change is the flux across the surface, Gauss's law, and you're done. For Euler's equation, you have to take the time derivative, you have to take the full time derivative, which is another application of chain rule to get the convective derivative. And then the pressure term comes from just arguing about pressure. There's several ways you can make that argument. Anything else? Did anybody have any questions about that? So this is mostly just getting your feedback on the ground. There's one thing, since I have this thing open, I'm going to show it. And this is the difference between group and phase velocity. No, go back. You don't even know what that's doing. So I'm jumping ahead a little bit here, but I've got, why did you go that way? That sucks.
I think you have to put the slider to the left.
Just give me the stupid gift. There it is. Okay. All right. So we're going to go through a non-trivial derivation about sound waves, and we're going to get sound waves. And these are the same sound waves that I'm speaking to you with. This is just how noise propagates in a room. So we're going to derive two different velocities. We're going to derive the group velocity and the phase velocity. And the phase velocity, Vp, is omega over k. I haven't said what omega and k are yet. I'll talk about those in a second, but this is just to put a graphic up so that you've seen the graphic. So the phase velocity is omega over k. So we're going to boost everything to Fourier space. So omega is the Fourier component that goes with time, that's the frequency, and k is the Fourier component that is the dual for space, so it's the spatial frequency. So the phase velocity is omega over k, and the group velocity, Vg, is d omega dk. This I'm not going to derive why this is today. I will probably do it on next Tuesday. It's a little bit involved about why we call the group velocity d omega dk. But the phase velocity is really easy to see. So the phase velocity, so I'm going to take a sine wave. I've got sine of kx minus omega t. I'm going to go through a little bit more detail about what this really means. Well, actually, let's talk about this for a second. So this is a wave that travels. So I've got a wave that looks like this. So if I hold t fixed, then I have sine kx. That's just a sine wave with a period kx. Does that make sense? So 1 over the wavelength is kx. If I hold space fixed, I have something that varies in time. So this will go up and down in time. Does that make sense? So if I take this and I draw another copy just a little bit above it for display reasons, and then this one. So if you take a point, you can see that a fixed point on my sine wave will travel up at a certain angle. So if this becomes the xt plane, then the velocity of a point on the wave is just going to be this angle. And what is that angle? I'm going to take, let's take this sine. This is sine of k times x minus vt, where v is the phase velocity, omega over k. I just did some algebra. I just factored out a k out of this, and I'm left with vt, with v phase. So you can think about this, x minus vt, as translation in time. So this is both the space and the time component at the same time in one package. And they're just related by the velocity. So a fixed point on the wave travels with the phase velocity. So that's this red square here in the graphic. The group velocity, if I have, so this is one wave with one frequency. We can call this monochromatic because it only has one frequency. If I have waves that have a spread of frequency, then I might have a wave packet where my wave looks like this. Right? So I have some combination of signs in here that all combine to give me this envelope of the packet. So you'll talk about this when you get to quantum mechanics, because what's an electron? An electron is a wave packet. An electron doesn't have a fixed wavelength. If it had a fixed wavelength, it would have to extend to forever. That's what Heisenberg tells you. This has a spread of wavelengths so that it can have this shape, and then this will travel. The packet will travel at the group velocity, d omega dk. I'll show you why the packet travels with that. So here, this point is fixed with the shape of the curve. So this point is traveling with the group velocity, and you can see it looks like the wave is traveling through it, but this is at the same point of this packet. So this packet is traveling, and the wave inside of it is traveling all at the same time. Does that make sense? No? It'll make a little bit more sense later, but that's the basic gist. Is we're only going to talk about one frequency, but because it's linear, I can add up a bunch of the same thing and get another answer. I'll explain what I mean by that in a second. But so this is the visual difference between group and phase velocity. Phase velocity is parked on a crest of the wave, and group velocity travels with the whole packet of waves. And one of these, the phase velocity, can be faster than the speed of light. There's no problem with the phase velocity being faster than the speed of light, but the group velocity is constrained by c, because the group velocity is what actually carries the information. The phase velocity doesn't carry any information. It's the actual packet shape that carries information. That's a lot more esoteric than we're going to get into in detail, but so we'll come back to group and phase in a second, and I'll show you where they come from. So now I'm going to turn that off.
Can you say what x minus vt is again?
Yeah, I'll talk more about that when I get there. Let me set it up and I said turn off? Oh, it says turn it off. Please wait. Okay, reading questions. So, yeah, I'll talk about all that in a second. Let me talk about reading questions. Oh, well, so the first question is that, which I'll talk about in a second. Second, why one-dimensional gas? Why do we care about one-dimensional gas? And there's several answers to that. So the first answer is because it's so much easier than doing things in 3 dimensions. Doing things in 3 dimensions is vastly more challenging than 1 dimension. So there's that old joke, the guy is looking for his keys under a light post outside of a bar, and another guy walks up and he's like, what the hell are you doing? He's like, I'm looking for my keys. And so the guy helps him look, and he was like, yeah, I lost them about 100 feet that way. And the guy says, well, why the hell are you looking here? He's like, well, because there's the light. The light's better here. So sometimes you gotta look where you have light. So we can do 1D hydrodynamics relatively easily. 3D hydrodynamics gets very difficult very quickly. But more importantly, this is actually a very general story. So if I have any reasonably large source of perturbations, then they will come out. So let's say I've got some. This is say waves coming off of the open ocean towards Jacksonville or whatever. They come out as basically planes. So if you've ever been over the ocean, if you've ever taken off from an airport near the beach, and when you get up high, you can really see that the ocean waves are really lined up pretty flat. This is basically one-dimensional. I mean, it's a 3-dimensional process, but I can treat this just as the up and down of these waves and rotate my coordinate system so that this is x, and then I'm basically in 1 dimension. So on one hand, it's easier to do it this way. On the other hand, it's a really great model for a lot of systems. And the third reason is training wheels. Like, it's easier to start with 1D than to jump straight into a 3-dimensional thing. Just for the pedagogy of how do these things fit together. So how does the dt and the dx, how do they fit together to make this sine wave thing? But that's an interesting question. What fluid gives the fastest sound speed? So I'll show you that the sound speed is equal gamma p over rho. P and rho are thermodynamic quantities. So since not everything has a density that changes a lot, but depending on what the mass density is and the pressure, if it's an ideal gas, you can rewrite that as gamma T times K Boltzmann over the mass of the particle. So, oops, squared, sorry. So C squared, and I'll show you why this is true. This will come out of the work that we do. So this will arrive. I'm just telling you now that this is how it is. So sound speed for an ideal gas is P over rho, which is just T over the mass of the particle. So the only things that matter for most gases are the temperature and the particle mass, not the actual density or anything else. It's just the temperature of the gas and how heavy the particles are. So ultimately, in outer space, in a big cloud of molecular hydrogen, you have basically the same sound speed because the temperature is a lot lower, but so is the particle mass. So in Earth, in the atmosphere, the dominant particle is N2, is a nitrogen molecule. In a molecular cloud, it's H2. So, so things wind up to give you a sound speed that's relatively 300 meters per second. But more questions. Relativistic, yes. If you want to do things relativistically, it's a different thing. You have to take all the relativity into account because this will allow you to go faster than the speed of light. Does the sound speed limit star formation rate? Because different sound speeds have different kind of compressiblenesses. And the answer is, I'm going to spare you the 4-hour lecture that I have on star formation rate. Mostly star formation rate comes from the turbulence in the gas, and it's a system process, and it comes from the chaotic environment of the cloud. So it does, but in a kind of very tertiary wave. Does gravity affect sound waves? And that is what we're going to do, not immediately next, but in a couple of lectures. Oh, he's not here. So to make gravity work, we just add on grad phi equals the acceleration of gravity. And then we're gonna do everything that we do today again with gravity, and we'll see kind of the basic equation of star formation. So you'll see. Why are we treating these as a perfect gas? Most things you can treat as a perfect gas unless something weird is happening. So like the air in the room, I can treat as a perfect gas unless I'm really trying to confine it or I'm trying to liquefy it. Or so a perfect gas can't turn into liquids. A perfect gas doesn't have any real size, so that if you're very dense, then the finite size matters. But for the most part, you can treat basically everything as a liquid or as an ideal gas. Water just has a very stiff equation of state. Water doesn't follow PV equals nRT, but you can still deal with it as a gas. So what we're talking about with continuity and Euler's equation works for any continuous fluid. Sand, if you have enough sand and the system is large enough that you're bigger than the particles. Entropy and enthalpy. So I'll come back to entropy and enthalpy. So they both have really deep physical significance that you'll get into. For this class, we don't need to worry about it too much because I'm never dealing with entropy as a quantity. Mostly when I deal with entropy, it's just going to be enough to say P equals root of the gamma and call it a day. So, and enthalpy is the internal energy plus the work it takes to make that happen. So it's kind of energy plus environment a little bit. So it's mostly, they're both other energies that you can deal with that have some value. Entropy is not an energy, but examples of acoustic waves. I am speaking to you with acoustic waves. So these acoustic waves are everywhere. And they're the key thing that happens in a fluid. If you have a fluid and you do anything to it, it will launch a sound wave. As soon as you disturb it a little bit, a sound wave will come out. So I move my hands around and sound waves come off. These are very low frequency sound waves. But it's still the pressure wave coming off of my hand. That's what keeps my hand from making a shock and cavitating and all kinds of weird stuff. So the pressure waves are all around us. What's a shock? A shock is when you're moving fast compared to the sound speed, and that's when you get a discontinuity in the density and other stuff. We'll talk about shocks soon. And we'll talk about supersonic flow too. One of you asked about supersonic aerodynamics, but I'm not going to get too deep into that because that's a whole other topic that I'm not super versed in. I don't know how to make planes fly supersonically, but we'll talk about other supersonic properties, including how to launch a ping pong ball faster than the speed of sound using a tube of PVC. How significant are the perturbations? So this is an important question. So the actual perturbations, so we're going to write down a system and then we're going to perturb it. The perturbations in a normal sound wave are very, very small, 1 part in 10 to the 6. So when I'm speaking to you, the density is getting a little bit denser, but only to the like 1 part in a million kind of size. Please explain the k-vector better. Group and phase velocity in k-vector, which I just did. And how does one determine a streamline? So that's an interesting question. So the streamline, if I have a flow, say I've got a waterfall, the streamline is just a vector field that is everywhere parallel to the velocity field. So I just draw a little vector everywhere where the velocity is going. So it might be something crazy and it's going to be highly time dynamic. But once you have the velocity field and the streamlines are you just connect the dots through the vector field. There are other kinds of lines you can draw. That streamline is not the path that the particle will take. It's the velocity field. A path line is the path that a particle will take, and that's harder to find because you actually have to integrate in the time dynamic sense. So I can take a snapshot of the streamlines here, but in 2 seconds down here where my waterfall is hitting my pool, the streamlines are going to be different because of the chaotic dynamics. The path line is not going to, it will instantaneously follow the streamlines at any point, but the streamlines might change, so the path line might be different. So, and then k-vector. So let's talk about k-vector for a second. So I drew this wave, and then I drew this vector. This vector is k. It's the vector direction that the wave is propagating in. So I have some function f of k, f hat of k, equals the integral of f of x, e to the I k x dx. This is a Fourier transform. I can make this a three-dimensional Fourier transform by making these guys all vectors, and this is a dot. So the analogy of this is we're writing things as sine and cosine, but sine of k dot x minus omega t. So this is not enough. This only has x. So we need to generalize our Fourier transform a little bit. So now our Fourier transform, we have f of x as a vector, and t is going to be the integral along d omega and d3k of, oh, I'm running out of the screen, aren't I? Oh, I'm totally on the screen. Back up and erase some crap. And I'll touch on all of these things again as I get to them. So if my answer to your question here is unsatisfying, I'll come back so there'll be more space to ask questions. So f of x is equal to the integral. We've got several integrals. D omega, d3k, f hat of k vector and omega, e to the I k dot x minus omega t. So this is the form, oh, this is f of x and t. So this is the actual Fourier transform that we're going to be dealing with. So nothing changes from what I said the other day. It's just an integral. But now we have more integrals. So now we have f of x and t, because the fluid in the room is a function of both space and time. And so we have corresponding variables. We have the k vector, which is the dual to the x vector. And you can see that these guys are up together up here. And the dual to the t vector, or to the t variable, is omega, which is this guy up here. So now k is a vector. And k, if I think about a wave, it's just the direction that the wave is going. Does that make sense? So, and this takes a second to get your head around. So we'll talk more about this in a second. But for the most part, I'm going to treat k like a scalar. X is a vector, k is a vector. They're dual to each other. But everything that we're going to do for the rest of this is going to be 1D. Okay. How am I on time? Good. So let's do sound waves. Let's do all of these things. So we start off with continuity. I'm going to try to write this clearly. Vt rho plus div rho v equals 0. And actually, let's write it up. dt of vi plus vj dj vi equals -1 over rho di p. Everybody happy with that? So the first thing we're going to do is, actually, let me make a roadmap of what we're going to do. Because there's a lot of things. There's a lot of steps in this. But there are a lot of steps that you do all the time. So in a textbook or in a paper, you might run across something that says, we begin with continuity and Euler. We linearize to first order, and do a harmonic analysis, and we get the phase velocity, Vp equals omega over k equals k equals dp d rho equals banana, right? And the group velocity, Vg, equals banana tree, right? So you're going to come across papers where they just do all the stuff that I'm going to spend the rest of the day on without telling you that they did it. I mean, they're going to say we linearized it, did a harmonic analysis, and here's the answer. Because it's really like, once you've done it a couple of times, you can kind of just look at a system of equations and linearize them. You don't have to go through everything that I'm going to go through here, because I'm going to go slow, but once you do it enough, you can do it quick. So it's a place for textbooks to skip a bunch of text and confuse the heck out of the reader. Also, it's where a lot of things come from. So, okay. So the first thing we're going to do is identify the background. What's the background solution that I'm perturbing around? So I have some state, and we're going to jimmy it. So we got to start with the background. And then we perturb, and then we throw out second order stuff. This step is important because this lets us turn it into something that we can solve with sines and cosines. Then we're going to combine two equations. So we're going to do a cross derivative, dt and dx, and then we're going to add. Then we add the two equations to get one equation. This step is specific to having a system of equations. So now we have a linear equation that's linear in my variables. And that's important because then we can do Fourier analysis. Which I'm going to go slow through, but once you get good at it, you can just say, oh yeah, all these omegas, all these d by dt's turn into omegas, and you just write down the answer. Yeah.
Can you repeat what is written on
4? 4 is combined. So we're going to take dt and dx of the equations, then we're going to add them together.
What's that bit up there?
This is an A and this is a B.
Okay.
So the first thing that we do, my graphic engineer is terrible. So this is the first thing that we do, and then this is the second thing we do. So this is just getting rid of an equation. So this is, you have two equations and two unknowns. You get rid of one of the equations with the other one. Now, instead of like when you did linear algebra, you would multiply and add. Now we're going to differentiate and add, but it's the same idea. Or if we're in Fourier space, it is just multiply and add. So the book is nice because he goes through this for sound. He does the same derivation a little bit differently when we get to sound with gravity, in I think an interesting way. So this isn't the only order of operations. You can spice things up a little bit. But that's basically what we're going to do. So the background solution. I know that for some rho naught equals constant, b naught equals 0. Now, whichever one of these you want to take to be first, you can look at continuity and see that it's true. If rho naught is constant, then this is 0, and the div of this is 0 only if v is 0 for an arbitrary case. Or, if v is 0, then d by dt is 0 and rho is constant. All this is saying is that the fluid's just sitting there doing nothing. So now, we're going to perturb it. We're going to say, so this is step 1. This is our background solution. So now, let me write my 1 over here. 2. Now we're going to perturb it. So everywhere, we're going to set rho equal to rho naught plus rho 1, and v equal to v naught plus v1. Oh, actually, let me sneak in real quick. real quick, I need to get rid of the pressure. So let's talk about the pressure for a second. So I know that pressure is 1 over rho dP dx. What's that?
What's the word before pressure?
1.5. That's my list. So I can rewrite this as if I know that P is a function of density only. This means the fluid is barotropic. There's many ways to do this, but the one way that happens most often is if it's adiabatic, and we know that P equals rho to the gamma. So I can replace dP dx with chain rule, call this 1 over rho dP d rho dx. That make sense? All I've done is a little bit of calculus, yeah.
That's P equals rho to the gamma?
Here, yes.
Okay.
Right? So I'm just going to, for now, we'll talk about more details later. For now, I'm just going to call dP d rho. We're going to call it C, and I'm not going to tell you what it is, but later on I'm going to tell you it's the sound speed. Here you can't tell that it's the sound speed, but you'll be able to see it when we get to the bottom. And dP d rho we can sort out. dP d rho is just, well, P equals rho T times K over M. This is just ideal gas law. So dP d rho is just T K over M. Okay. So there's this quantity C that we'll use, and it's dP d rho, and it is equal to, oh, sorry, squared. We're going to call this C squared. It needs to be squared. C squared is dP d rho equals T K Boltzmann over the mass of the particle. So we'll need that later. And then we're going to change this. This now equals minus 1 over rho. It equals C squared over rho grad rho. So I started off with 3 equations and 2 unknowns, so I have to get rid of one of these variables, and pressure is the variable that we'll get rid of. Does anybody have any questions about that? Basically, all I'm doing is a little calculus, and if I don't know how P depends on rho, this is all still true. This part is because it's an ideal gas, the second equation. Okay, so got rid of pressure. Now we have 2 equations and 2 unknowns. And we're going to perturb it. So now I'm going to write both of these equations again in the perturbed state. So I get d by dt of rho naught plus rho 1 plus div rho naught plus rho 1 times v naught plus v1. Now, we stated already that v naught is 0. So this is just dropping in everything, but let's simplify this a little bit. This just becomes a v1 equals 0. And let's expand the other one. So all I've done is said, okay, I know rho naught is a solution. I'm going to expand it by rho 1 and v1. Rho 1 and v1 are small, very, very, very small. So now let's take Euler's equation. So this becomes d by dt of v1 plus v1 grad v1. Okay, if I were going to install everything, I would have a v naught plus v1 here and a v naught plus v1 here. Ultimately, that is how you do a Galilean boost. So if you want to look at fluid while you're flying past it very fast, then you would need to say v naught is not 0. V naught is some constant in some direction. We're not going to do that. We're going to skip a step. Just say that v naught is 0. So I've got this term becomes d by dt of v1. This one is v1 grad v1. And then I'm left with minus 1 over rho naught plus rho 1 times d by dx of rho naught plus rho 1. Okay. Does anybody have any questions about what I've done so far? We all right? Now let's throw things out. So now we're on, so this is step 2. So now we're on throw out the second order stuff. So let's go cross out stuff we know. What's d rho, what's d rho naught dt? 0. What's, oh, now we gotta expand this. So we'll expand this as grad rho naught v1 plus rho 1 v1 equals 0. Now I'm gonna throw out all the things that are small twice. So what I get to throw out is this rho 1 v1, because that's 2 small things. Now when you're doing this for homework, if what you want to do is say this is epsilon times rho 1 and then throw out every time an epsilon v1, and everywhere throw out anything that you have that's epsilon squared, that's a fine bookkeeping way to do it, but I just keep track of how, I just need to have 1 subscript 1 in every term, and if there's 2, it goes away. And then this term, this guy is fine. This guy has 2 v1s. Now we get to throw out the nonlinear term, yay. And then this term, okay, so this one, what is grad rho naught? It's constant. It's constant, so it's 0, right? And then I have a grad rho 1. Okay, we got to deal with this 1 over rho naught plus rho 1 equals, got to do a Taylor series. So how do you do a Taylor series on that? This is one of those Taylor series that you should probably just remember, but I don't always. If I have x plus delta to the minus 1, I'm going to take the derivative with respect to x, and I get 1 over x plus delta squared times delta. And you do it right, and this rho naught, rho 1 at the bottom becomes squared and it goes away. So this term, because it's in the bottom, is just rho naught. So you can do that with a Taylor series.
We can also just multiply it onto the other side and just take rho away.
Yeah. A simpler way to do it. That's better. If I multiply this over here, this term's gone, and this term is going to be rho naught plus rho 1. And this is going to be a rho naught times dv dt rho 1. That's just got 1 tiny. And the rho 1 times dv dt rho 1, dv1 is tiny. So our linearized equations don't look a lot. Here, I'm gonna erase these guys and write up the linear equations. So our linearized equations don't look a whole different. We got d by dt of rho 1 plus div rho naught v1 equals 0. And d by dt of v1 equals minus 1 over rho naught grad rho 1. Oh, what did I miss? C squared.
Could you explain how you got rid of the rho 1 v1 term?
This one?
No. Like
This one?
Yeah.
It's small.
Okay.
So this is epsilon twice. So at rho 1 and v1 are both of the order of 10 to the minus 6. So this is the order of 10 to the minus 12, so it goes away. That's an important stunt. So that step of throwing out all the second things, that's where a lot of physics is done. So I went through it kind of quick because it's actually not all that hard, but it's important to think carefully about what you're throwing out and when. So now I've got this system of equations that is linear in all of my perturbed quantities. This is not linear in my perturbed quantities. I got 2 perturbed quantities here. This is not linear in my perturbed quantities. I've got 2v1. So both of those get hard to solve if you're trying to actually solve. So this is now our new system of equations. Yeah, okay. Does anybody mind if I erase this? As with everything, I might not think to ask if anybody minds if I erase it before I start erasing it. So holler if I do start erasing something that you still need to see. So now what do we need to do? Now we need to combine these 2 equations. I got 2 equations and 2 unknowns. I've got a d by dt of rho 1 and a grad of v1, a d by dt of v1 and a grad of rho 1. So I need to take the space derivative of this one and the time derivative of this one. Nope, other way around. What am I getting rid of? I'm going to get rid of V. I want an equation for density. So I need this term to look like this term. Let's put this on the other side. Equals 0. Let's do it. I'm just going to move this to the other side of the equation and get a plus there. So I want to get rid of this term and this term. So I need to make them look like each other. So I need to take the time derivative of this guy and the space derivative of this guy, and then I have the same thing. So then I've got d1 d by dt squared of rho 1 plus, let's pull that rho naught outside, dt dx of v1 equals 0. Let's multiply through by rho here. So I've got rho naught dx dt v1 plus c squared dx squared rho 1 equals 0. So I take the time derivative of this and the space derivative of this, and now I subtract because I've got this term. This term is the same as this term, so now I can subtract, and I'm left with d by dt squared of rho 1 minus c squared d by dx squared of rho 1 equals 0. So now I just have one equation, and it's linear in rho, so I can solve it with Fourier transforms. So does anybody have any questions about getting to this point? Does that all seem basically straightforward? So now how do we solve this? Sines and cosines. It's always sines and cosines, right? So we're going to say that rho 1 equals some amplitude, and this is another free parameter, but this is really a boundary condition that shows up, times e to the I kx minus omega t. So the book just says we're just going to assume that the solution looks like this, which seems like a pretty bold assumption. But that's actually not what he's doing. What he's doing is something that's very general. What he's doing is he's saying that rho 1 equals the integral of d omega dk, we only have one k right now, of rho hat of k and omega e to the I kx minus omega t. We're just taking this Fourier transform of this other thing. Let's call this, I called it rho a before. This is rho a, which is a function of omega and t. Now, if you do this, so now I'm going to take this and plug it into this equation. And then I'm going to get something on the inside. And then that has to be equal to 0, and then I can throw out the integration because the inside has to be 0. The integral is 0 for an arbitrary integration bound, so the inside is 0. But we can kind of skip that step by just saying, I'm just going to say this is my solution. So we're just picking one Fourier mode to plug in, rather than all of them. So this is an integral over all the Fourier modes. Does that make sense? But the modes don't interact with each other right now. Why do the modes not interact with each other? Because we threw that interaction term out. So if you do this again with the whole equation, then it gets really ugly, but you'll get an equation that has different amplitudes at different frequencies that are interacting with each other. That's way more complicated than what we want to deal with. So we're just going to deal with one frequency and say that rho 1 is some amplitude times e to the I kx minus omega t. So when I plug this into here, my d squared by dt pulls down a minus I omega twice. So that gives me just minus omega squared. So this term turns into A1 minus omega squared, and then, sorry, rho A. Sorry, let me rewrite that again. Minus omega squared rho 1. It gets itself again, right? And then this term gives me a minus, and I get a plus c squared of, I've got, again, a minus, I get 2 i's, k squared times, again, rho 1 itself. So, rho 1 cancels, because rho is not 0. And I'm left with this equation. Omega squared equals c squared k squared. Does that make sense? You good?
Yeah.
Okay. So, what does this mean, and what do I do with it? Like, what does this tell me? This is some math stunts that I could pull, but really this tells me exactly how the fluid behaves. So, what this tells me is if I disturb the fluid with some frequency, it's going to produce waves of this wavelength. So if I have a bucket of water and I just put some jiggles into it, I'm going to get waves that launch out at a certain frequency. Let's think about that for a second. So what is this C? So if I make a motion like this, it's going to translate into a motion like that. But this is going to be traveling at some velocity, c. So when I make a motion, if you just think about like a drum with paper on it, rolling at a certain velocity, and I start jiggling it, the wave that comes out, and I start drawing on it in a back and forth motion, the wave that comes out will have a certain length based on how fast the drum is moving. That makes sense? This is the same thing. The length of the wave that I make with this perturbation omega is going to have a velocity, or is going to, because I have a velocity c, the length of the wave is going to be determined by omega. And so for sound waves in air with nothing else going on, I'm just left with omega squared equals c squared k squared. So now let's talk. I'm going to talk again. So here I've done all these things, but let's talk. Let's actually recap, and then I'm going to interpret what we did a little bit. So we started with our system of equations, which is horrible and nonlinear, and fundamentally and famously does not have a well understood solution space. So this equation, no, this one does, but Euler's equation does not have a well constrained solution space. It's not like the heat equation where we always know what's going to happen. We don't always know what's going to happen. So we have these horrible equations. We have some background solution that we know is true. We do a little bit of algebra to make sure we get rid of things. Then we perturb it by saying my background solution plus a little tiny thing. Do that everywhere. Throw out all the second order stuff. And then you're left with a linear equation. Then do a little bit of algebra, just so that you only have one equation. And then do the Fourier analysis. And then understand the Fourier analysis. So let's talk about understanding the Fourier analysis a little bit. Let's rewrite what we got here. So we have omega squared equals c squared k squared. And while I've written down a whole bunch of steps, this is one of those things that you wind up doing a lot. And it's the same kind of process all the time. Or you do it once and then you build your whole theory based on that linearized solution. So let's talk about this sine of kx minus omega t. So when I do this Fourier transform, this is the eigen-nugget. This is the eigenvalue of the Fourier transform is a sine and cosine. So the sine and cosine is built, sorry, not eigenvalue, basis function. This is the basis function that I'm doing this linear transform. So you remember doing basis transforms in linear algebra? How many of you guys are taking linear algebra?
We did basis transformations.
Okay, cool. So you've done basis transformations. This is the same thing, except instead of instead of having a vector space like this that you transform to a vector space that looks like that, we have a vector space of functions that we're turning into another vector space of functions by rewriting them with sines and cosines. And we've got one in both. So let's talk about this for a second. So this, we can talk about sine of k x minus vt. And one of you had asked about this a second ago, and I said I'd get back to it. So now I'm getting back to it. So what this says is this is a thing that goes up and down with some wavelength k and some phase, whatever this is. Now this is x, but it's x, it's translating x. So it translates with time. So if I think about a point, let's say at t equals 0, my wave looks like this. This point is going to translate if I now, let's do it in another color. So this is amplitude in t space. Now I'm going to write an x space. So this is x for both of those. This is time. So this is going to travel upwards as this whole thing translates this way. This point will just travel along this angle. And that angle is given by the velocity. So the velocity makes an angle with the time axis of that. So a higher velocity gets you a steeper angle, and the thing will translate along faster. But all this is a sine. This is just sine k theta, where theta is now this thing that has some space component but also moves, and those two things are related like this. So this v is v phase. So this v is vp equals omega over k. It's the velocity that a crest or a trough will move at in the fluid. Okay, does that make sense? Does anybody have any more questions about this yet?
So will the angle for the velocity be different at a different time?
No, that's a good question. So this stays the same. So this is always going to translate in time at the same rate. And you can tell because, I don't know. It doesn't have to. So you can write down a scenario where the phase velocity will change in time. You can write down a scenario where the phase velocity, so Vp is c for us. So for us, the phase velocity, look at omega over k, is just c. There are scenarios, and I think I'm going to make it a homework assignment, and you'll notice that I threaten more things with homework assignments than actually happen, but this is a good one. If we, instead of having a big universe, we say we have a floor to our ocean, and we talk about the height of the ripples, then we get a dispersive system. So this is non-dispersive. All waves travel at the same velocity. Did I say that? Have I said dispersion relation out loud yet today? This is called the dispersion relation. This is called the dispersion relation. And if it's constant, then we call it non-dispersive. That means that if I set up a packet of crazy bullshit, then as it translates, it's going to be that same packet of crazy bullshit. If I can draw my squiggles exactly the same, right? It hasn't dispersed at all. But if we do this with waves on the top of the ocean, and I'm either going to do it or have you do it just so that you see it get done, you find that the phase speed is equal to the square root of k times some c squared thing. So what that means is that different wavelengths travel at different speeds. So I start off with some crazy bullshit here, and then later on, I'm left with all the big waves, and then all the little waves show up first. So this is how surfing works. This is why you can surf in Southern California, but you can't surf in Southern Florida. The surf in South Florida is wretched, but the surf in Southern California is great. Why? because of the planet. So if you have California here, here's Baja, and you have Australia here, the ocean is dispersive. So when I have a storm down here by Australia, the ocean does this amazing job of filtering different wavelengths of different sizes out so that they arrive at different times because they travel at different speeds. A storm is noise. It creates wavelengths of all different sizes. But the ocean is a nice filter because it's dispersive, because the dispersion relation tells you that different waves travel at different speeds. All the short waves will show up at one point in time, but then a couple days later you get these nice, perfectly spaced waves that just come in one after another, and you can catch them. Yeah.
So that's like tsunamis, right? Why you get the bigger waves later?
No, any storm.
But also
Regular
like,
storms.
they can-
Tsunamis are impulsive events typically that create one big delta function.
Okay.
So usually that's a kind of a step function that travels like a shock. I'm trying to ask that question again. I'm curious. I haven't thought too much about tsunamis and how they relate to all this. Yeah.
By the ocean being dispersive, you mean it like just like mellows the storm out a little bit over the?
No, it filters. It's a filter. So it's like filtering waves into different bins. So it takes a packet of waves that has a whole bunch of waves, and it sorts them in time. So it sends out all the short waves first, and all the medium waves later, and then all the long waves last. And now that's what happens after the process. I mean, it's a process of filtering. So once you get up to the other side of the planet, then you've had enough time to filter things out. But it acts like a filter.
Like a Fourier transform?
In Fourier space, yeah. Yeah, it's a Fourier filter.
And the reason that we don't get good waves in Florida is then because the storms are too close.
No, because there's all these islands. So Florida's out here. Florida looks like this, and you have the Bahamas and the Virgin Islands down here,
It's regular.
and they totally jack everything up. So you can't see the open ocean really from South Florida. But North Florida's okay. North Florida's okay because you can see other parts of the ocean. That's why like Cocoa Beach is such a slanted surf spot. St. Sebastian or Sebastian Inlet, like there's great surf spots up in North Florida because it's not blocked by these other waves. But the waves that make good surf come from the open ocean and get dispersed and filtered to make to make a decent wave up here. So it all comes from this dispersion relation. So the dispersion relation that we got here, so we do all this math and then we get this omega ck business, which has nothing to do with velocities. So why is this a solution? This is a solution because it tells you how the system behaves in response to input. And it tells you how things travel through the system. Bless you.
Thank you.
Okay. Sure. Is there anything else that I need to talk about today? Yeah.
So you're calling it like a filter because
Yeah.
the small waves get there first.
Yeah.
So how is that different from just like decay?
Well, because the wave doesn't go away. That's a good question. The wave doesn't go away. It's still there.
But it's smaller.
Yeah. So it's no. The wave is the same. So we start off. Let's talk about a distribution of waves. So when I have, so that's a good question. Let's take that apart. So I start off
That's cool.
with this wave and this wave, and they're at the same space. And then, actually, let me do this in different colors. So the storm makes a wave that looks like this. And I can break this into, let's just pick two, I can break this into big waves and short waves. And actually, let me be a little bit more careful about this. Let's just draw one, and then two. So these guys get born in the same space, so they're cohabitating right here in the same space. And so what the wave is doing is not this plus this, is not this and this. It's the sum of those two, which is going to be something complicated. Right? After time, then I'm left with this wave is in front, of this wave. But the waves are the same amplitude. So the wave itself hasn't decayed in size. It's just been shifted from its compatriots. It's like segregation, or which is a perfectly legitimate word. And yet we live in the South with all of the baggage of American history. So they get separated into different classrooms. Maybe I shouldn't make segregation jokes. So they get separated into different time bins, but they don't go away. So dispersion is different from diffusion and is different from decay. So I'm glad you asked that question, because that's important. Because they get used pretty similarly too. So because if I'm only sensitive to one particular wavelength, then it does, and I'm traveling along this wavelength, then it would look like decay to me, because the smaller wavelengths are disappearing from the population. So it would look like they're going down, but in fact they're just getting spit out. Jake?
And this only happens in the ocean because the dispersion relation is omega goes like root K.
Yeah, because omega goes like, or VP goes like the square root of K. Jesus Christ. VP equals square root of K. It's communication issues all over the place. Rather than for sound waves, it's C squared, and this is a constant. So that's the difference, is this depends on K, but this one doesn't. Santiago?
So if you know your system very well, and you want to just exclude all of the small waves, for instance, and you only want the big wave, you can set something up to I guess, destructively interfere with the small waves, and then once that's done, you just focus on the big waves?
Yes, that would be in addition to dispersion. So that would be some kind of active noise cancellation. So that's basically how noise cancellation works. Yeah.
So C is omega over K, right?
It's also T.
Okay, but C depends on K as well, right? Are you saying that the ratio of omega
Oh,
to
yeah.
K is
Omega
always
over
constant?
K is VP. So when I write omega over K here, all I'm left with is C. But when I do it for the deep water waves or shallow water waves, then I get something that's not C. I get something that looks like omega squared equals C squared K cubed. So when I do omega over K, I'm left with a square root of K.
Okay.
That makes sense? So we'll see a more non-trivial dispersion relation in a minute. Maybe I'll just do that on Tuesday. Yeah.
Does the air also do this with sound waves?
It does, to an extent. And it does it, and because the Earth is a sphere and the upper atmosphere is ionized, you can use things like this to communicate over distances. So they use that as well. But the air isn't super dispersive. It's not like shallow water. Now you can make air dispersive by giving it boundary conditions. Boundary conditions really change things.
So is that air dispersion, can that make certain pitches of sound louder or softer? Because let's say you're listening to an orchestra and you hear two instruments playing relatively the same pitch, but different octaves. So would that make one ring louder because of the dispersion of the air?
No, it's time. It's all about timing. You would get all of the tuba sounds first, and then the flute sounds. So you would hear the same amplitude for everybody, but different pitches would arrive at different times. And now I'm wondering how fun it would be to cook up some dispersion relation and pretend that the air is dispersive and run some noises through it. I could do that in Python in a couple hours. I think it'd be really hilarious. I'm going to totally forget about that. That's such a cool idea. Anyway.
For the sound of instruments to get
Oh,
to write
I forgot to write
separately,
that.
it would take a long distance, right?
Yeah, but it takes distance for that to happen. So it wouldn't happen just if you're in the room. That's okay. Just put it in the comment of your homework.
Okay.
I haven't graded anything yet, so. you
No,
just-
I forgot to ask about the, why you record a guitar strings.
Oh, right.
I
You forgot about that. I forgot about that too.
No, yeah.
Well, let's shoot me an email or something. and
I'll
try
write
to-
it
yeah.
in the next reading.
There's another reading coming up next, so yeah, that's a good one. Okay, I think that's all I got for today.